G'day, Internet. For the third installment on improving your secure code review skills, I'm going to recycle a presentation that I gave at Countermeasures a while back. It was a virtual presentation, and I don't believe it's been released to YouTube. So I thought I'd re-record it. And the reason why is I feel this lays better fundamentals before I move on to some of the other break classes and the other methods that I use for code review. Yeah, here's how you do bug hunting with grep. Who am I? You can read that online. Sitting in the way of justanotherhacker.com. And when I say bug hunting, the objective that I usually work towards is collect enough information to identify vulnerability that will get me code execution on the books, or a CVE identifier for the vulnerability. I won't really touch on CVE. That's probably a whole subject of its own. And the process is quite simple. It's to find a vulnerability candidate in source code. grep is the filter that filters out most of the source code and only presents us with the areas that we're interested in, the potential vulnerability candidates. And ultimately, human analysis is required to verify whether or not something is a risk or not. And when we do code review, it's a bit like looking at a code through a tube, a paper roll, or a pipe. You're only focusing on a small area of the code at the time. You're not trying to understand the entirety of the code base. Only enough small pieces to put together a proof of concept. And the process, it's iterative and recursive, I guess. You grep the code for some data points, you analyze what grep returns, then you adjust what you're looking for next, or you adjust your rules so that you get less noise. You grep again, and then analyze again. Rinse and repeat until you have enough information to solve the puzzle. And obviously, a lot of people start their code review journey with grep, and you often compete with things like SAST or DAST. And so the question might be to grep or not to grep. I personally like grep. I use grep a lot, and it has some clear benefits. A lot of SAST tools require the code to compile. So if you're missing a little piece of code, you have to jerry-rig something to make it compile so you can run the analysis. Whereas grep can be used on partial code, it can be used on diffs, it can be used on what you're able to extract from a broken zip file. You don't require the entire code base. It's very versatile and consistent across different platforms. So whether you run it on Macs, on Linux, on Unix, Windows, it's pretty consistent. That changes a little bit with regular expressions, but most of them have some form of regular expression support. And grep, and I guess to some extent the regular expression, they're very good at text matching. And luckily for us, most programming languages are text-based. And because we're doing text matching rather than, analyzing code on a semantic level, it's very easy to add support for new languages or frameworks. And typically grep will present you with text, so it shows you the code directly. You don't have to sit and use a management interface or a PDF report and then cross-reference what's in the report to the code. It's showing you the code directly. And for me, that works really well. Obviously, grep also has some limitations, particularly multi-line matching. So if you have an SQL statement that spans multiple lines, grep won't see that as one string. It sees it as a lot of individual lines and won't get the semantic understanding of this is one string. It also doesn't have a really semantic understanding of whether a piece of text is code that executes or it's a commented out piece of code. And obviously the data that you get back and the amount of noise or false positives is only as good as the regular expressions you use when you correct the code. And there are a lot of tools that are similar to greps, but aren't greps. For example, coccinelle will give you pretty good semantic understanding, but can still do string matching. Semgrep, similarly, semantic grep. That's pretty new, it's pretty popular. And ripgrep, it's like grep, but it has things like support for git ignore by default. They're all similar. You can substitute greps for your preferred method. I like to use just plain grep. The reason for that is, as a pen tester, you'll often end up on a box that you don't control the toolchain for. And so relying on just the basic grep rather than a more advanced setup can be beneficial in those cases. So why don't we start with something simple, like getting a CVE with grep. That's quite simple. One of the simplest way to get a CVE, in my opinion, is to spot code that fails to verify SSL certificates when they're making an outbound request, or I suppose these days TLS validation. So this is specifically for PHP, but it tends to be pretty common. And I won't go into the historical reasons for that. But you'll find this a lot. It's never, almost never, a false positive. So if you see this code, you have yourself a vulnerability, and you can request a CV for that vulnerability. Very low effort work, but yeah, it's pretty easy to get one. Now, if you want to take advantage of a lot of the regular expressions that I've already done, I'll get a grep-based tool, and you can find that on GitHub. There's also a tutorial on using Rodit on the YouTube channel. Although I'll cover a lot of the same things in this talk. So typically the output of Rodit is approximately this. This screenshot is from an older version, but it's largely the same. And this one highlights what I call my indicators, what I look at, the importance of it, etc. So the most important thing to look at is the thing that I'm sitting right in front of. So let me just move myself. Right. So right there, we have the vulnerable code, or the vulnerability candidate within code, and that in this case is a local file include. It's a limited local file include. You can't control the file name, only the directory for which you look for the file name in, and you can't do remote file includes. It's a limited local file include. The other things that I like to look at is the file name. So in the case of index.php, that's usually indicative of it potentially being publicly accessible, that you don't need authentication to reach it. The other thing I look at is the line number that it occurs at. In this case, it's 299. And that's important because there's usually a control flow that the program follows in order to reach the vulnerable line of code. And if the code is a library, that's probably only the function definition that's around the vulnerable piece of code. But if it's a common file like index.php, where it's usually running top to bottom and not being a lot of functions, you might have to pass through a lot of requirements. Examples of such requirements is you might need to be an authenticated user, otherwise the code will never reach the vulnerable line. You might have to have a certain value in the cookie, in addition to being an authenticated user. And so the further down the line number is, usually the more preconditions exists in order to reach the vulnerable piece of code. And that's a very quick way to analyze whether or not a vulnerability candidate is a good candidate for further investigation, whether it can be easily exploited. It's not guaranteed to be difficult just because it sits on a higher line number, but it's usually a good indicator. And the last thing I look at is how many findings there is within the one file. So this big line here shows that everything is index.php. And again, in the case of an index.php file, that may not be so important, but if it's, say, a class file, it's usually an indicator that a lot of functions within that class file is vulnerable, and as such, it's more likely that you'll find a call path that goes from publicly accessible file that then loads an instance of that class and then calls a vulnerable function with a parameter that the attacker controls. So that's the basis of the output. And recognizing the highlighted lines, that's something that comes with experience. So before I look at some more examples, we'll talk a little bit about regular expressions. For grep, there's typically 3 types of regular expression. There's basic, which is more or less just text matching. There's extended, which supports character classes as the predominant differentiator. And then it's Perl compatible regular expressions. And the biggest difference, I guess, between extended and Perl compatible regular expressions is both the syntax, so that you're not using character classes by name, but like you can do \d for digits. And also one of the big ones is the ability to use a range indicator to say that we want to match 5. We want to match 5 characters that are digits rather than 6, or you can't just use the plus or the asterisk symbol to quantify the number of matching characters, but you can specify between 3 and 5. You can't do that in extended. And the regular expressions, or rules as I call them, though in Gorode, matters. At its simplest form, anyone can just open a text file and write a bunch of keywords that are name of functions within the language, such as in PHP, require can lead to local file includes or even remote file includes. So let's look for require. And unfortunately, that's also a common English word, or reasonably common English word. And so you'll get a lot of false positives. And how do we reduce those false positives? Well, we refine our query. So we look for require with parentheses around it. And even more so, we want require with a variable in it, because if it's just a string glitch or all of like include library.php, the attacker can't control any of the data that's used in the path for require, and as such, it's not valuable to us from a code review perspective. So we want to make sure that we do the escape $sign in there. And again, if you're not reviewing PHP, let's say that you're reviewing a language like C or Java for Python, where variables don't have a sigil, you'll probably just have to put up with a lot more false positives. Again, you can do things like filtering out strings based on the first character inside the parameter to require. But the idea is that you want to tweak the regular expression to the point where it filters out the noise. And of course, in PHP, it's not just require that can lead to this problem, but the function require once. So then the next level of analysis is to do both require and require once. And then the final level is to really expand this. And so I've shortened require with the optional ones instead of require or require once, just in order to save horizontal space as I'm writing the code. I'm making an optional space before the start of the parentheses, just because some people might put a space before the parentheses in a function called it's valid syntax in PHP. So you've got to be able to support it, even though you might not write code that way yourself. And in fact, the parentheses is optional. You can do require space string. And then we want to make sure that there's a variable, and ideally we want a variable that we know that the attacker is almost guaranteed to be possible to control. So get, post, request, cookie, they're almost always user control. Environment can be a hit and miss. And so the last iteration of this will be far less noisy than the previous iterations. And so investing time in improving your regular expression is a great way to make bug hunting with grep a more enjoyable process and reduce the amount of noise you have to deal with. One example of this was a while back now, I ended up having to review some server-side JavaScript or AMT script, which is a variant of JavaScript that Salesforce supports. And you want to find SaaS tools generally that support this. And so it's pretty easy to look through their function name, look for things like parameters from the URL or the query string, look for functions that deal with things like XML or base 64 encode, decode, or lookups for database information. And then we could write out a set of regular expressions like this, run that against code and identify some vulnerabilities. Overall, I'd say there's probably a day's worth of effort to put together the regular expressions, then running it, getting some false positives, and then refining it. But it didn't take too long to build this up. And again, you can see here, the initial list was just keywords like lookup and attach file and barcode URL. And then based on the code that we're looking at, you identify places where it misses things due to, capitalization, or you're getting far too much information back, because things like lookup is a common word. And so then go through the step of adding more syntax quantifiers to limit the noise and only get relevant information back. And so it's this process of you run the graph, you analyze, you adjust, you graph again. And I use this for Crawdit as well. I maintain multiple different databases. And so at the bottom, there's a lot of like Crawdit, flatline and Crawdit fruit that have low noise ratios with usually what it spits out is likely to be a vulnerability candidate, but it also limits what it looks for, and so you might have some false negatives code that it misses. Whereas Grodded -PHP generates a lot of noise. And so typically my approach is to start at the bottom and then work my way up. So start with the low noise rules, slightly noisier rules, slightly noisier rules. And sometimes I also look for specific bug classes like Grodded -PHP SSL tends to look for specific bug classes. And then that way I can focus. And so when I run the later, the noisier rules, I already know, oh, I've read that file, I've looked at that piece of code before, it's safe, and cross-referencing my notes, it means that I don't have to start chasing stuff as much. I can just go, yeah, look at that, skip it, skip it, skip it. And we can see the different outputs here in terms of what we're looking at. The backtick variable finding here tends to be from PHP, but it also matches on JavaScript. Obviously, the difference is in PHP it would be a code execution vulnerability. In JavaScript, it would generally be a cross-site scripting vulnerability, or possibly code injection vulnerability. And here's more of a specific example where we're basically auditing MySQL queries or SQL statements only. And so again, you can focus very easily on a specific subset of vulnerability classes. And you can see here again, I'm sitting over it down the bottom, SQL injection, assuming that the attacker controls the URL ID variable and that it has not been escaped. Also at the top there, in the file upload, if the GPX server ID is user controlled or the GPX user ID is user controlled. Yeah, that's good. Now we've looked at SQL injection before, so I'm not going to dwell on this. This one is slightly different. So this is running a specific custom really annoying. The aircon keeps turning on. So this is using a specific rule where if I go back, where you can do echo rule type Grodded -d hyphen, which reads from standard in, or data standard in, which is the more portable way of doing this. So this particular piece of software, CMS, whatever it is, has a get parameter function that gets a parameter from the query string, and so by just doing echo get param and passing it into Grodded, reading from standard in, we can identify a number of places where this parameter is used, such as in SQL injection statement, or sorry, SQL injection, used in SQL statement resulting in SQL injection, such as limiting the offset parameter. This is I think the flatline or the fruit rules for C and C++, and what we're seeing here is, well, gets is never a false positive. Should not be used in modern programming because it cannot be handled safely. And again, more specific rules. This I'm running in the colorblind mode, so the colors are a little different, and identifying specific queries. Now, one of the interesting things here is up there, there's the second findings where we have a multi-line SQL statement. Now, we said earlier that grep doesn't understand multi-line strings. But what I have done is I've identified the ways in which SQL statements are usually broken up across multiple lines, and so I've written specific rules for only the where clause, or only the and or clauses, or the limit clause of SQL statements, and as such we can find vulnerabilities in a multi-line string, even though grep doesn't have a semantic understanding of it. Simply by tweaking the regular expressions, we can still identify vulnerabilities in those cases. So yeah, when all you have is a hammer, when all you have is grep, everything looks like a net. So, like I said, I use grep a lot. I use it to do stuff that grep probably shouldn't be used for, like regular expressions for things like secrets, where we can find different ways of identifying password hashes or plain text passwords, private keys, etc. Obviously, scanning for secrets is not new. There's a lot of tools that does it, but if you're already using grep, you might as well use grep for this as well. It works quite well. Taint analysis. So when we're tracing something from a source to a sink, usually this is done with fancy, expensive SaaS tools, or to some extent open source SaaS tools. And essentially the way it works is we track taint, or whether or not a variable or value is user controlled, and you trace that from one function into the next function into the sink. So in this case, the argument value that comes from a command line argument that's traced into string copy using a multi-step process. And we can use grep to do taint analysis. This one only does one level deep. So what it does is it runs grep PHP, massages that through Perl to generate new grep rules on the fly based on what it's seeing, and then pipes that back into grep to scan again. And we can see this working here, where the variable TID gets set from the user controlled get ID. And then the second instance where we see TID used in an SQL statement, that has been commented out, and it's not a vulnerability. And just below that, we see the updated SQL statement where they're using parameterized queries. Very good, nice and safe, not vulnerable. And we see again on line 49, it's been used to generate a report header. Would have to investigate that further to determine whether or not that's a vulnerability, but we can skip it for now. And then again, I am skipping over the good part. So let's move me. And we see that on line 55, there's a consecutive query using the same variable. And because we're tracking the variable name, every instance of that variable in the file is reported. And so if there was another assignment or any sort of input validation on that variable, we would see it, and we're not. So in this case, we can tell that the initial SQL injection on line 36 was replaced and fixed with parameterized SQL injection. Oh, sorry, parameterized queries, which is not vulnerable to SQL injection. Details matter. However, they didn't fix the secondary use of the variable in an SQL statement on line 55. So this is a failed remediation. And so you go from SQL injection in one particular query, patch that, and then the subsequent query is vulnerable. So my preferred way of finding vulnerabilities is to use AutoTaint, where the sink and the source is on the same line, because grep does line-by-line analysis. So if the sink and the source is on the same line, you don't have to do taint analysis. The taint analysis is already there. Right? And that is what my fruit and flatline databases try to do. Here's some examples where it reads file content from user home plus a user control file name. So you can just // etc password, and you will read etc password. Now that's a arbitrary file read. It's not local file include because the function is file get contents. It is not an include or require statement. You cannot leverage this one for code execution because it's an appended value. So the user home will prevent you from using streams. And as such, you cannot leverage that one up into code execution. So it's not a local file include or an LFI, as people would often say. This is one of the commonly misclassified vulnerabilities that I see. It's just an arbitrary file read. And the next one obviously is a database query, and again, the SQL statement and the user control value in $get is on the same line. And so there's no need for taint analysis. And one of the benefits, of being bug hunter or doing this for vulnerability research purposes is that you can kind of keep swapping out code bases until you find something. You don't necessarily have to dig into a specific code base like you would do if you were a paid consultant or an internal security team, where you have to review your source code. You don't just keep choosing source code until you find one that has a vulnerability. Right. So what about taint on other languages? Because I do a lot of PHP. So here's a simple example that does basic taint analysis on C. It does this by defining character array, feeds that into Broadit, and then feeds the output of that Broadit into Perl to extract the identifier of character arrays, puts that into a temporary file, reads those ones out, and generates rules containing memcopy, string cat, string copy, as printf, and the variable name, and puts that into standard in, so feeds it back into Broadit, feeds that back. Anyway, so it does a lot of like in and out of Broadit and Perl and files, basically just feeding the data back onto itself and modifying the taint. What it's trying to do is to limit variables. We only care about variables that end up in a sink. We don't want to track all the sources that aren't ending up in a sink. You just end up with too much noise. And that's why it seems like, if you're able to follow this code, it seems like it's running the same queries 3 times, which essentially it does. But the reason for that is to reduce the noise. And if we ran that, we can see some examples here where this table exists, CBP SQLite database interface. It does a sprintf into a string with no checks on the function parameter set table, and as such you have SQL. Well, you both have SQL injection and buffer overflow. I would prefer to exploit buffer overflow because code execution is better SQL injection in my opinion. And again, the next example defines a file name of 50 characters, and then calls string copy on that. And the thing to notice here is there's an in file name and an out file name, if, of, and then they're the same size. So the string copy is essentially the same of the same length, which wouldn't be a buffer overflow. Just fill out the buffer, but then it does a string cat afterwards of .ecs, and that will get you 4 bytes past the array. Although you cannot control the value necessarily. It's a DOS if it was a service, although I believe in this case it's a command line utility, so it's not a very useful bug, but it illustrates that the functionality of the script to do taint analysis with grep works. And like I said, the benefit of being able to choose code bases is handy and allows us to do bug hunting at scale. So I wrote a basic tool that runs git scan, const URL, and does a basic scan on it. And also you can look for git logs, you can look for existing vulnerabilities. And again, I looked at a different approach to this using the GitHub interface in the first instance of this series in episode 1. This is the command line equivalent, where I'm using grep to look at the git log to find vulnerabilities. And so again, you can run this, you can see how they've done it, and you can then, one of the ways you could leverage this is to look for SQL queries that don't have database escape lines around them. So again, you can do Grodit or grep to find SQL. Use the -c parameter to give it more lines above and below, and then grep for instances that doesn't have database escape. And back in the day, many years ago now, I used to run a scan every day that would look at updated PHP repos. It would run the flatline rules and do some basic taint analysis. I started this, as you can see from the lines here, on the 1st of October 2016, and I finished this on the 6th of December 2018. It didn't run every day, although I think some days it skipped, but it's a bit over 2 years, or 793 days in total I had output for. And within that time, it found 88,818 vulnerability candidates. Obviously, processing all of those would have taken a lot of time. I did process a lot of them. I got a lot of CVEs in that period of time, but most of them ended up unreported because the vulnerability reporting and disclosure process is very time-consuming. A lot of the repos I scanned, obviously, were just homework and hobby projects that has no users and it's not worth reporting for. So it was obviously a review process every time, but yeah, that's approximately 112 vulnerabilities a day for vulnerability candidates. So if you want to have an indication of how much code I've reviewed over the years, this is largely what has contributed to my ability of looking at the output of Grodit and saying, yeah, that's a vulnerability. No, that's not a vulnerability. Sort of gut feeling, just off the top of my head, is because I have looked at many thousands lines of code, and I've run Grodit a lot of times to get all of this output. And obviously, that's just the initial reporting. Obviously, from that point on, if a particular repo was interesting, then I'd download it and I'd go through and do a more thorough code review. So in conclusion, vulnerability discovery doesn't have to be advanced. As we saw at the very start, you can grep for SSL TLS misconfiguration, you can get a CVE super easy. You don't have to be particularly skilled at it. And again, I think I hope it was evident in episode 1 that you can identify a pattern from known vulnerabilities, reapply it, and find unpatched vulnerabilities within the same repo. Or cases where, like we saw in this presentation, where someone's fixed a particular instance in a file of SQL injection, but they haven't fixed the subsequent query. And obviously, some bad classes are much harder to detect than others, particularly logic ones. Or so I'm planning to look at logic bugs in episode 4. Hopefully, I'll have that one out soon. And usually, finding the vulnerability is usually only the start of the journey, right? You'll proceed. You'll find more vulnerabilities. You'll have to do you usually want to do a proof of concept to illustrate that it's an actual risk and that it can be exploited. You might have to deal with a vendor, do disclosure, etc. There's often many other steps after you find the vulnerability. Yeah, questions, since this is not a live presentation. If you have any questions, suggestions, comments, etc., leave them below, and I'll hopefully address them at some point. Thank you and goodbye.